Welcome to RGES Algebra 2. This is Lesson 8A. Your assignment will be the check for improvements for 1 and 2, Tests 1 and 2, at the end of Chapter 1, getting ready for your Chapter 1 test. On Wednesday, we will go over any questions you have before we begin the test. And then your new work will be 2.1, 1 through 7, and 2.2, 1 through 15. This is talking about more about multiplying. Okay. Well, actually, factoring is really where we're going into next. All right, factoring is the basic idea for this unit. In section 2.1, we're going to review the concept of factoring. We can find, first off, all factors, and second off, we can find prime factors. All factors or prime factors. And this should definitely be review for you, but let's go ahead and recall the vocabulary associated with these ideas. Let's say our number is 24. Well, to find all factors, I am going to do everything that divides into 24. And I like to do it by pairs. 1, we always have a 1. 1 times 24 will be 24. 2 times 12 will be 24. 3 times 8, everything that goes in evenly. Does 4 go in evenly? Yes. Does 5 go in evenly? No. And then I get actually back to my 6, which was my next number. So when I'm listing all factors, I would simply list them all in order. 1, 2, 3, 4, going back up, 6, 8, 12, and 24. And that would be the answer you're looking for when you ask for all the factors of a number. Now, when I'm talking about prime factors, recall what primes are. Primes are any number that its only multipliers are 1 in itself. So my first prime, the only even prime, would be 2. And I'm not looking at the problem yet. I'm just listing primes. 3 is a prime. 4 is not a prime because 2 divides into it evenly. 5 is a prime. 6 is not a prime. 7 is a prime. 8 is not a prime. 9 is not a prime. 10 is not a prime. 11 is a prime, 12 is not a prime, 13 is a prime, 14 is not, 15 is not, 16 is not. From now on, all my even numbers will not be because they'll be divided by 2. 17 is a prime, 18 is not, 19 is a prime, 20 is not, 21 is not, 22 is not, 23 is, etc. And so I'm trusting that you remember these are the prime numbers, and you can just keep going up for quite a while in your head, probably. But if we ask then for prime factoring, I'm saying factor this number 24 into only prime numbers. So I would take, there's 2 ways to do it, but I would like to take it by the tree method, and hopefully this jogs your memory. I would just think of any 2 numbers that multiply together to give me 24, and the first things that come to my mind are 4 and 6. Neither one of these are prime, however, so 4 is 2 times 2. Now 2's are prime, so when I get to my primes, I'll circle them. And 6 is 2 times 3, and 2 and 3 are both primes. So I have divided this number now into its prime factors, which would be 2 times 2 times 2 times 3. And that would be the answer if I were to ask you to prime factor these numbers. Now, a little bit more vocabulary when it comes to 2.1. When we talk about the degree of the second term, okay, that's kind of silly, but that's all right. Let's say we go well, first off, I will identify the second term, and the degree is found by the exponent, so that would be the second degree. And that's all they mean there. State the degree of the polynomial. Well, let's say I have x to the 4th minus x squared, or minus y squared minus 2. I have to define the degree of each term. This would be the 4th. This would be the 2nd. Okay. This would be a first degree. And which is the largest? Well, it happens to be the first one, the fourth. So you're just picking the largest degree of any term, of all the terms, the largest degree, and that would be the degree of your polynomial. Now, monomial factoring. You're asking what is common, so now we've already moved on to 2.2. When we're doing monomial factoring, we're asking for what is one term that divides evenly into all the terms given. It's almost like thinking distribution in reverse. Okay, so if I have the example nx plus ny plus nz plus, well, that's all. Okay, and I've got three terms here, and I'm asking what divides evenly into all of those. This would be the same as n. And what would I have left over in my, so to speak, if I were to make this a distribution, I would need an x plus a y plus a z in the parenthesis. Okay, so let's do a few more of those. I like to do these very simply by first looking at my numbers. 3, 6, and 9 all divide evenly by 3. How many a's do they all share? Well, they all share one a. Okay, because not all of them have two a's, right? And how many x's do they all share? One x. So what would I need to multiply the first term by to the 3ax by to get the first term? And notice what I'm missing is I'm missing the a. Copy my signs. 3 times what equals 6? So 3 times 2. I already account for my a in my multiplier out front, and I need one more x. Copy my sign. 3 times what is 9? 3. I already account for my a, and I account for my x. Now what am I saying here? I'm saying that if I distributed, I should get what I began with. 3a squared x minus 6ax squared plus 9ax. So hopefully that's very clear to you. So we are doing, so to speak, the opposite of distributing. We're trying to take out the largest thing they have in common. Let's look at one more. 3xy squared minus 6x squared y to the fourth. Number, the largest dividing evenly would be 3. X's, they both have one x in common, and they have two y's in common. Now what am I going to do with this? Because that's the same as this. So I better put a 1 in there so that when I distribute back, I'll get that first term. My multipliers for the second term will be 2x y squared. So you can prove that to yourself simply by distributing back, and you'll get the first one. All right, I think that's fairly straightforward. I'd like to look at these word problems together after you have tried to do them. So try to do the word problems on your own and then come back. That would be, go ahead and do 1 through 11, actually 1 through 12, and do that deliberately, and then try to do 13, 14, 15. Put this on pause until you're finished with your homework. We will give you the answers for the first 12 in class, but I'd like you to look very carefully with me at 13, 14, and 15, because this sometimes stumps students the first time through. I'd like to first look at the sample problem. It says Jared is 3 times as old as his brother Jesse. 3 years ago, he was 6 times as old as Jesse. What are their ages now? Now, there's a little bit of a trick, perhaps, in the way you first go about thinking about this. I'm going to create myself a chart. I'm going to talk about Jared and Jesse. And I know that now Jared is 3 times as old as his brother Jesse. So if Jesse is X, then Jared is 3X. And that's pretty straightforward, right? And then I want to talk, however, about what it would have looked like 3 years ago. Well, notice everybody would be 3 years younger then. So Jesse would be 3 years younger, and Jared also would be 3 years younger. So I'm going to take this value here, and I'm going to plug in every time I see the x, I will now plug in the new expression for the x. So it would be 3x minus 3. Okay? So if this was x going up to 3x, this would be 3 times what Jesse was then. Actually, it says he was 6 times as old. I apologize. 3 years ago, he was 6 times as old. Let's correct that. Think for a second, how would you correct that, by the way? No, actually, for my expressions, I did it exactly right. Now I'm going to use that 6 times in the equation. Okay? So how does that work? Well, it says he was 6 times as old as Jesse. Okay? Oh, I do apologize. Let's go back and do this one more time here. I'm not thinking very, very clearly. So hopefully all my confusion will help you in the long run to solve yours. All right. All I care about right now is not the relationship between them, but that it was 3 years ago. So Jesse 3 years ago is going to be what he is now minus 3. And Jared 3 years ago is going to be what he is now minus 3. There we go. Okay, now to get my equation, it says 3 years ago, so I'm going to be working my equation in the past, what they were in the past. He was, he meaning Jared. Jared was 6 times as old as Jesse. So where's Jared in the past? There's Jared in the past. There's Jared 3 years ago. Jesse 3 years ago is here, and Jared was 6 times as old. Okay, so there's part of from the word problem. Right? And this is Jesse in the past. Okay, so you have to make sure with these, Jesse, you have to make sure that if I'm dealing with one in the past, I'm dealing with the other in the past. The columns are in this chart are important. So now I can simply solve it. I'll solve it by distribution. 3x minus 3 equals 6x minus 18. I'll pull that to the left. Negative 3x. I'll pull that to the right. Negative 15. And x equals 5. Who is x? Okay, well that is Jesse. So my question, by the way, you should always look for a question. What are their ages now? Jesse is 5 and Jared is what? Go to the now table and it's 3 times that, or 15. Okay, so after showing you that one very carefully and trying not to make any more mistakes, let's go on then and try to show you 13, 14, and 15. Well, this is not as complicated, number 13, because I'm only dealing with one person, not two. But I am dealing with a now and then. So let's make my chart, an abbreviated chart here. If he's X now, what was he then? Well, then was 12 years ago. Okay, now for my equation, 12 years ago, a boy was, so what was his age 12 years ago, or then? Was, same as my is, same as my equal sign, 1/3 what he is now. How old is he now? So hopefully that's pretty clear to you, and once you do that, you can solve it quickly. So I finished it up there for you, and trusting that you're not going to have trouble with the actual solving, I always do like to label what's going on here in these age problems. Let's look at 14. Okay, the 14 says in 2 years, James will be twice as old as he was 2 years ago. and how old is he? So this is a little different because we've got the now is our x. In 2 years, what would he have been 2 years ago? He would have been x minus 2. What would he be in 2 more years? It would be x plus 2. And now we're ready to write our equation. In 2 years, that's the future, he will be twice, so take my future. Will be, notice whenever I get that verb form, that shows me my equal sign. In 2 years, he will be twice as old as he was 2 years ago. That's my past. And once you can figure that out, it's a pretty straightforward problem then to go ahead and solve it. Now x is 6, and notice when I define my x, that's how old he is now, and that's what they're asking. So he's 6 years old right now. Okay, let's try the last one, which will be the more complicated one, and we'll need more of the chart that's similar to the one in the sample. Okay, so we're talking about the father and the son, we're talking about now, and we're talking about in the past. A father is 4 times as old as his son, so if I make the son x, the father will be 4x. Now what's going to happen 6 years ago? Well, 6 years ago he will be 6 years younger, and 6 years ago he will be 6 years younger. And therefore, that's the way we do the chart. Now, let's pull out the equation. It says 6 years ago, he was, let's see, we're talking about the father or the son. We're talking about the father. 6 years ago, the father was. So, what's the father 6 years ago? The was, my verb, is going to be my equal sign, 7 times as old as his son. Now, am I talking about the son now or the son then? We're talking about the son in the past. If one's in the past, the other's in the past. So 7 times as old as his son. And that's my equation, and then I can solve it. Now part of the problem is interpreting. Once I got x equals 12, what is that? We'll go back up to where x is. That is the son now. So what's the father now? We're asking how old, find the age of each. If the son is 12, the father is 4 times 12. So this is the son, and the father is 48. Okay, so look over those again if you need to. Those tend to be fairly complex for students, so go over them very, very carefully. Try to work them a couple times as though you're seeing them, maybe on 2 or 3 different days before you come back.